far beyond Earth, orbiting the giant planet Saturn, lies a small icy moon called Enceladus. For centuries, it appeared to be nothing more than a frozen world drifting silently through space. But everything changed in 2005 when NASA's Cassini spacecraft made an astonishing discovery. From deep cracks in the moon's south pole, enormous geysers of water and ice were erupting into space. Powerful plumes blasting material hundreds of kilometers above the surface. When Cassini flew directly through these plumes, it detected water, organic molecules, and the chemical ingredients for life. Beneath the frozen crust, scientists now believe there may be a global ocean of liquid water. And new discoveries are revealing that this tiny moon may be far more active and far more mysterious than we ever imagined. Before we continue, subscribe to Theories Before Sleep for more deep space mysteries. Because tonight, we explore the latest discoveries on Enceladus and the extraordinary possibility that life could exist beneath its frozen surface. In the vast darkness of the outer solar system, far beyond the warmth of the sun, Saturn reigns as one of the most magnificent worlds known to science. Its enormous rings stretch across hundreds of thousands of kilometers, forming one of the most breathtaking sights in our cosmic neighborhood. Orbiting within this complex system of rings and moons is a small, bright world that for most of human history attracted almost no attention. Its name is Enceladus. At only about 500 kilometers across, Enceladus is tiny compared to most planetary bodies. In fact, the entire moon could fit comfortably inside the state of Arizona. For centuries, astronomers assumed that such a small object, located so far from the sun, must be little more than a frozen, inactive chunk of ice and rock. After all, the surface temperature on Enceladus is unimaginably cold. Sunlight reaching this distant region of the solar system is extremely weak, and temperatures can plunge to around minus 200 degrees Celsius. In an environment like this, liquid water should not exist. And yet, today, Enceladus is considered one of the most promising places in the solar system where extraterrestrial life might exist. But this remarkable transformation, from an overlooked icy moon to a potential cradle of life, did not happen overnight. It took centuries of discovery, decades of exploration, and one extraordinary spacecraft mission to reveal the secrets hidden beneath the ice. The story begins in the late 18th century. In the year 1789, the famous astronomer William Herschel was carefully observing the planet Saturn through one of the largest telescopes ever constructed at the time. Herschel had already made several remarkable discoveries, including the planet Uranus and multiple moons of Saturn. During these observations, he detected a faint object orbiting close to Saturn. This small point of light would later be identified as Enceladus, one of Saturn's many natural satellites. But through Herschel's telescope, Enceladus revealed almost nothing about itself. It appeared as little more than a tiny, distant speck of light. For nearly 200 years, that remained our only view of this mysterious world. Even with improved telescopes and advances in astronomy, Enceladus remained extremely difficult to study. Its small size and great distance from Earth meant that it never revealed many details about its surface or structure. For a long time, scientists assumed that Enceladus was simply another frozen moon, similar to many other icy bodies scattered throughout the outer solar system. But in the late 20th century, everything began to change. In 1980 and 1981, NASA launched two spacecraft that would revolutionize our understanding of the outer planets, Voyager 1 and Voyager 2. These robotic explorers were designed to fly past the giant planets, Jupiter, Saturn, Uranus, and Neptune, sending back the first close-up images ever taken of these distant worlds. When the Voyager spacecraft passed through the Saturn system, their cameras captured the first detailed images of Enceladus. What scientists saw was surprising. Instead of a heavily cratered ancient surface, like most small moons, the images revealed large regions that were unusually smooth and bright. In fact, Enceladus turned out to be one of the most reflective objects in the entire solar system. Nearly 100% of the sunlight that strikes its surface is reflected back into space, giving the moon an almost pure white appearance. But brightness alone was not the only strange feature. Some areas of the surface looked remarkably young, with very few impact craters. In planetary science, a lack of craters often indicates that geological activity has recently resurfaced the terrain. Something on Enceladus appeared to be reshaping the moon's icy crust. This discovery puzzled scientists. How could such a small world remain geologically active? Normally, small moons cool quickly after their formation. Without internal heat sources, they should become completely frozen and inactive over time. Yet the surface of Enceladus seemed to suggest the opposite. There was another mystery as well. Voyager observations showed that Enceladus was located within Saturn's E-ring, one of the planet's outermost rings composed mainly of microscopic ice particles. This ring was unusually dense around the orbit of Enceladus itself. Some scientists began to suspect something remarkable. Perhaps Enceladus was somehow feeding material into Saturn's ring system. But at the time, there was no clear evidence explaining how such a process could occur. The mystery would remain unresolved for more than 2 decades. Then, in 1997, NASA launched a spacecraft that would transform our understanding of Saturn and its moons forever. This mission was called Cassini. Cassini was one of the most ambitious planetary missions ever attempted. The spacecraft was designed to orbit Saturn for many years, studying the planet, its rings, and its diverse family of moons in unprecedented detail. After a long journey that lasted nearly 7 years, Cassini finally arrived at Saturn in 2004. Almost immediately, scientists began planning close flybys of Enceladus. At first, these encounters were expected to confirm the earlier Voyager observations, perhaps revealing minor geological activity beneath the icy crust. But what Cassini discovered instead shocked the scientific community. In 2005, Cassini's cameras detected something extraordinary happening near the moon's south pole. From long fractures in the ice, later nicknamed tiger stripes, enormous geysers were erupting into space. These jets of material were blasting water vapor, ice particles, and gas hundreds of kilometers above the surface of the moon. Enceladus was not just geologically active. It was exploding with activity. The plumes were so powerful that they were ejecting roughly 250 kilograms of water and ice every second. For scientists, this was a breathtaking discovery. Not only did it confirm that Enceladus possessed internal heat, but it also provided a rare opportunity to study material coming directly from beneath the surface. Normally, exploring the interior of a distant world requires drilling through kilometers of rock or ice, an incredibly difficult task for robotic missions. But Enceladus was essentially spraying its internal ocean directly into space. Cassini could simply fly through the plumes and analyze the particles. NASA quickly changed the mission plan. The spacecraft was directed to perform extremely close flybys of Enceladus, sometimes passing just tens of kilometers above the surface. During these daring maneuvers, Cassini flew directly through the geysers erupting from the Moon's south pole. Its onboard instruments began analyzing the composition of the plume material. The results were astonishing. The spacecraft detected water vapor, confirming the presence of liquid water somewhere beneath the surface. But it also found something even more intriguing. Mixed within the icy particles were organic molecules, carbon-based compounds that are considered essential building blocks for life. Even more surprising was the detection of molecular hydrogen. On Earth, hydrogen gas is often produced by interactions between seawater and hot rock near hydrothermal vents on the ocean floor. These vents support entire ecosystems of life in the deep ocean, even in complete darkness. Could something similar be happening beneath the ice of Enceladus? The possibility electrified scientists around the world. But the discoveries did not stop there. Over the next several years, Cassini continued to gather data during repeated flybys of the Moon. Scientists began analyzing the gravitational behavior of Enceladus and tracking subtle movements of its icy surface. What they discovered revealed something even more extraordinary. Beneath the frozen crust of Enceladus lies a global ocean of liquid water. This ocean appears to surround the Moon's rocky core entirely, hidden beneath a thick shell of ice. In other words, Enceladus may contain a vast underground ocean stretching across the entire Moon. For planetary scientists, this was an incredible revelation. Until then, oceans had primarily been associated with planets located within the so-called habitable zone, where temperatures allow liquid water to exist on the surface. But Enceladus lies far beyond this region, in one of the coldest environments in the solar system. So how could liquid water remain stable beneath the ice? The answer appears to lie in powerful internal forces. Enceladus is locked in a gravitational dance with Saturn and several neighboring moons. As it orbits the giant planet, gravitational forces constantly stretch and squeeze the Moon. This process, known as tidal heating, generates friction within the interior of the Moon. That friction produces heat. Over millions of years, this heat appears to have melted large portions of the ice inside Enceladus, creating the hidden ocean beneath its crust. But the story becomes even more fascinating. Evidence suggests that the ocean floor of Enceladus may contain hydrothermal vents, where hot water interacts with rock deep beneath the ocean. These environments are extremely important in the search for life. On Earth, hydrothermal vents are home to thriving ecosystems of microorganisms that rely not on sunlight, but on chemical energy released from the planet's interior. If similar vents exist on Enceladus, they could provide both energy and nutrients, two critical ingredients for life. And that brings us to one of the most profound questions scientists are now asking, does life exist within the hidden ocean of Enceladus? To answer this question, researchers look for 4 key ingredients necessary for life as we understand it. First, there must be liquid water, which acts as a solvent, allowing chemical reactions to occur. Second, there must be a source of energy, capable of driving biological processes. Third, the environment must contain the chemical elements necessary to build complex molecules. And finally, life requires time, long periods during which chemistry can evolve into biology. Remarkably, Enceladus appears to possess all 4 of these ingredients. And as scientists continue analyzing the vast amount of data collected by the Cassini spacecraft, new discoveries are still emerging, revealing that this small moon may be far more complex and fascinating than anyone ever imagined. But the most surprising discoveries about Enceladus were still yet to come. If Enceladus truly contains a vast ocean hidden beneath its icy shell, the next question scientists must answer is an obvious one. How deep is this ocean? For many years after the Cassini mission began studying the moon, researchers believed that the liquid water might exist only in a small pocket beneath the South Pole. This idea seemed to fit the observations at the time because the giant geysers erupting into space were concentrated in that region. The South Pole appeared to be the center of the activity, but as scientists continued analyzing Cassini's data, subtle clues began to suggest that something much larger was happening beneath the surface. One of the most important discoveries came from carefully tracking the shape and motion of the moon itself. Like many moons in the solar system, Enceladus experiences a slight wobble as it orbits Saturn. This wobble, known as libration, can reveal valuable information about the internal structure of a planetary body. By studying the tiny shifts in Enceladus's rotation over several years, researchers noticed something strange. The moon was wobbling more than expected. If Enceladus were a completely solid object, its rotation would be relatively stable. But the data suggested that the icy crust was not rigidly attached to the rocky interior. Instead, it appeared to be floating on liquid. This observation led scientists to a remarkable conclusion. Rather than a small, regional ocean beneath the South Pole, Enceladus may actually contain a global ocean that surrounds the moon's rocky core entirely. Imagine an entire world where a frozen crust floats above a dark, hidden ocean. Beneath that ocean lies a dense rocky core, slowly releasing heat and chemicals into the water above. It is a structure unlike anything found on Earth. And yet, in many ways, it might still resemble environments where life thrives in our own planet's oceans. But understanding the structure of Enceladus was only part of the puzzle. Scientists also needed to understand how this ocean remained liquid. After all, Enceladus is incredibly far from the Sun. The sunlight reaching the Saturn system is nearly 100 times weaker than what we experience on Earth. Under normal circumstances, any water present on such a distant moon should be frozen solid. Yet the plumes erupting from the South Pole clearly showed that liquid water was present somewhere beneath the ice. So where was the heat coming from? One possibility was radioactive decay inside the moon's rocky core. On Earth, the slow breakdown of radioactive elements generates heat deep inside the planet, helping drive volcanic activity and plate tectonics. But calculations suggested that Enceladus's small core could produce only about 1% of the energy needed to power the observed geysers. That meant another source of energy had to exist. The answer once again appears to lie in the powerful gravitational influence of Saturn. Enceladus is tidally locked to Saturn, meaning that the same side of the Moon always faces the giant planet. But the orbit of Enceladus is not perfectly circular. Instead, it is slightly elliptical. As the Moon moves closer to Saturn and then slightly farther away during each orbit, the planet's immense gravity repeatedly stretches and squeezes the Moon. This constant flexing generates internal friction, and friction generates heat. This process is known as tidal heating, and it can produce enormous amounts of energy over long periods of time. Inside Enceladus, tidal heating likely warms the rocky core, allowing water to circulate through the cracks and pores of the rock itself. When this water is heated, it rises upward through the ocean above. Eventually, it reaches the underside of the icy crust near the South Pole. There, pressure builds beneath the fractures known as the tiger stripes, and when that pressure becomes strong enough, the water escapes violently into space. These towering geysers are the visible signature of a hidden ocean system operating deep inside the Moon. But perhaps the most exciting discoveries came when scientists began analyzing the chemistry of the plume particles themselves. Cassini carried an instrument called a mass spectrometer, which allowed scientists to identify individual molecules within the particles flying past the spacecraft. As Cassini flew through the plumes, this instrument began detecting a wide range of chemical compounds. First, scientists confirmed the presence of water vapor and tiny ice grains. That alone was already remarkable. But the instrument soon revealed something more complex. The plume material contained organic molecules, carbon-based compounds that form the foundation of biological chemistry. These molecules included hydrocarbons containing combinations of carbon, hydrogen, nitrogen, and oxygen. These elements are not random. In fact, they are part of a set of 6 chemical elements considered essential for life as we understand it. Scientists often refer to them using the acronym CHNOPS. The letters represent carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These 6 elements form the basic building blocks of biological molecules such as proteins, DNA, and cell membranes. Finding several of these elements inside the plumes was already exciting, but the story became even more interesting years later. After Cassini's mission ended in 2017, scientists continued studying the enormous amount of data the spacecraft had collected. Advanced analytical techniques allowed researchers to re-examine the mass spectrometer readings in much greater detail. And in 2023, a major breakthrough was announced. Scientists confirmed the presence of phosphorus within the plume particles. This discovery was incredibly important. Phosphorus plays a critical role in biological systems on Earth. It is a key component of DNA, RNA, and cellular energy molecules like ATP. With the detection of phosphorus, Enceladus now appeared to contain all 6 of the chemical elements necessary for life. In other words, the hidden ocean beneath the ice might possess the complete chemical toolkit needed to support biological processes. But the surprises did not end there. More recent discoveries have come from a completely different spacecraft. one that never even traveled to Saturn. High above Earth, orbiting the Sun nearly 1.5 million kilometers away, the James Webb Space Telescope has been studying distant galaxies, stars, and planets. But scientists realized that Webb's powerful infrared instruments could also observe objects within our own solar system. So researchers decided to turn the telescope toward Enceladus. What they saw was astonishing. Webb detected a massive plume of water vapor erupting from the Moon's south pole. This plume was far larger than anything previously observed by Cassini. In fact, the vapor cloud extended nearly 10,000 kilometers into space, stretching far beyond the Moon itself. Even more surprising, this plume appeared to feed a vast torus, a donut-shaped ring of water vapor that surrounds Saturn. The material released from Enceladus slowly spreads throughout the Saturn system, contributing to the composition of the planet's rings and magnetosphere. In other words, this tiny moon is actively reshaping the environment of an entire planetary system. It is an extraordinary level of influence for such a small world. And it raises another important question. How long has Enceladus been active? If the ocean beneath the ice has existed for millions or even billions of years, then there may have been enough time for complex chemical processes to occur. Time is a critical ingredient for life. Even on Earth, it took hundreds of millions of years for the earliest biological systems to emerge after the planet formed. So scientists are now trying to determine whether the geothermal activity within Enceladus has been stable over long periods of time. Recent studies analyzing thermal data from Cassini suggest that the Moon's heat output matches the expected energy produced by tidal heating inside the core. If these models are correct, the ocean beneath Enceladus may remain liquid for a very long time, perhaps long enough for life to begin. And that possibility has transformed Enceladus into one of the most compelling targets in planetary exploration. Future missions are already being proposed to return to the Saturn system and study this mysterious moon in far greater detail. Some mission concepts involve orbiters designed to repeatedly fly through the plumes, collecting samples of the ocean material. Others propose landers that could touch down on the icy surface near the South Pole. One particularly ambitious concept even involves sending a robotic probe capable of melting its way through the ice, eventually reaching the hidden ocean itself. If such a mission were successful, it could directly search for microscopic life forms within the alien sea beneath Enceladus. And if life were discovered there, it would represent one of the most profound discoveries in the history of science. It would mean that life is not unique to Earth. Instead, biology might emerge naturally wherever the right conditions exist, even on small frozen moons orbiting distant planets. But for now, Enceladus continues to keep its deepest secrets hidden beneath kilometers of ice. Yet with every new observation, every new analysis of Cassini's data, and every new telescope pointed toward the Saturn system, scientists are slowly uncovering the story of this remarkable world. And the deeper we look, the more extraordinary that story becomes. One of the most fascinating aspects of Enceladus is that scientists did not discover all of its secrets during the Cassini mission itself. In fact, many of the most important discoveries about this moon have emerged years after the spacecraft finished its work. Cassini collected enormous amounts of data during its 13 years orbiting Saturn. The spacecraft performed multiple flybys of Enceladus, sometimes passing only a few dozen kilometers above the surface. During these encounters, its instruments captured measurements of the Moon's gravity, magnetic environment, plume particles, and surface temperatures. But analyzing this data is an incredibly slow and complex process. Each flyby produced large datasets that scientists have been studying for years. As new techniques and computer models become available, researchers are able to return to the same measurements and uncover details that were not visible before. And in the case of Enceladus, this ongoing analysis has continued to reveal surprising new insights. One of the most important discoveries came from studying the tiny ice grains within the plumes. When Cassini flew through the geysers erupting from the Moon's south pole, some of the ice particles struck the spacecraft's instruments at extremely high speeds. These collisions shattered the particles into fragments, allowing scientists to analyze their chemical composition. At first, the data showed mostly water ice and relatively simple molecules. But as scientists continued examining the measurements with improved analytical tools, they began identifying larger and more complex organic compounds. These molecules were far more complicated than scientists originally expected. Some contained long chains of carbon atoms combined with hydrogen, oxygen, and nitrogen. Others formed ring-shaped molecular structures similar to those found in biological chemistry. These discoveries were significant because complex organic molecules are often considered the building blocks of life. They can participate in chemical reactions that eventually lead to proteins, amino acids, and other structures necessary for living systems. However, the presence of organic molecules alone does not prove that life exists. Organic chemistry can occur naturally through geological processes without any involvement from biology. But the complexity of the molecules detected in the plumes suggested that the ocean beneath Enceladus may be chemically active in ways scientists had not previously imagined. Another important clue came from the salinity of the ocean. Scientists were able to estimate the salt content of the hidden ocean by analyzing sodium-rich particles within the plume material. These particles appeared to originate from water that had interacted with rock deep inside the Moon. By modeling these interactions, researchers concluded that the ocean beneath Enceladus is likely moderately salty, similar to Earth's oceans. This result strengthened the idea that water is circulating through the Moon's rocky interior. When ocean water flows through warm rock, it can dissolve minerals and transport chemical elements back into the ocean environment. This process creates a constant exchange of materials between the rocky core and the liquid ocean above. On Earth, similar processes occur at hydrothermal vent systems along the ocean floor. These environments are rich in minerals and chemical energy, making them ideal locations for microbial ecosystems. The possibility that hydrothermal vents exist beneath the ice of Enceladus is therefore one of the most exciting aspects of the Moon's environment. But scientists wanted to know whether the chemistry inside the ocean could support biological reactions. One of the key requirements for life is the presence of certain chemical elements that form the basis of biological molecules. Researchers often refer to these elements using the acronym CHNOPS, which stands for carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These 6 elements make up the vast majority of living matter on Earth. For many years, Cassini's data had already confirmed the presence of several of these elements within the plume particles. Water vapor revealed hydrogen and oxygen. Organic molecules confirmed carbon and nitrogen. Sulfur-containing compounds were also detected, but one crucial element remained missing: phosphorus. Phosphorus is extremely important in biological chemistry. It forms the backbone of DNA and RNA molecules and plays a critical role in energy transfer within cells. Without phosphorus, life as we know it cannot exist. For a long time, scientists believed that phosphorus might be scarce in Enceladus's ocean. If that were the case, it could significantly reduce the moon's habitability. But in recent years, researchers revisited Cassini's mass spectrometer data with improved models of how molecules fragment during high-speed impacts. By carefully analyzing the patterns of ionized particles detected by the spacecraft, scientists identified evidence of phosphorus compounds within the plume material. This discovery was announced in 2023 and immediately captured the attention of planetary scientists around the world. With phosphorus confirmed, Enceladus now appeared to contain all 6 major elements necessary for life: water, organic molecules, energy from hydrothermal processes, and the complete set of biological building blocks. It was an extraordinary combination. But scientists still needed to understand how stable these conditions might be over time. Life requires not only the right ingredients, but also long periods during which chemical reactions can gradually become more complex. To explore this question, researchers began studying the moon's internal heat flow. Cassini's instruments had measured the temperature of Enceladus's surface in great detail, particularly around the tiger stripe fractures near the South Pole. These measurements revealed that large amounts of heat were escaping from the interior of the moon. But scientists wondered whether this heating was a short-term phenomenon or a long-lasting process. Recent studies combining Cassini's thermal data with models of tidal heating have suggested that the energy generated inside Enceladus could remain stable for extremely long periods. The gravitational interaction between Saturn and its moons continually flexes Enceladus, generating heat through internal friction. As long as this orbital configuration remains stable, tidal heating could continue warming the moon's interior for millions or even billions of years. If that is true, the ocean beneath Enceladus may have existed for a very long time, and that dramatically increases the chances that complex chemistry and possibly biology could develop within its waters. But while scientists were still analyzing Cassini's data, another powerful instrument was preparing to observe the Saturn system from far beyond the planet itself. This instrument was not orbiting Saturn, it was orbiting the Sun. And it was about to provide an entirely new perspective on the mysterious activity of Enceladus. High above Earth, the James Webb Space Telescope had begun its mission to study the universe with unprecedented sensitivity. Although the telescope is primarily designed to observe distant galaxies and stars, its infrared instruments are also capable of studying objects within our own solar system. Scientists realize that Webb could observe the water vapor released by Enceladus's plumes. So they turned the telescope toward the tiny moon orbiting Saturn. What they discovered was astonishing. The plume of water vapor erupting from Enceladus was far larger than scientists had ever measured before. Webb detected a massive cloud of vapor extending thousands of kilometers into space. This plume was not just a small jet escaping from the moon's surface. It was a gigantic structure spreading water across the entire Saturn system. These observations confirmed that Enceladus is constantly releasing material into space. Some of this material forms the E-ring surrounding Saturn. Other particles become trapped in the planet's magnetic field, contributing to a vast cloud of charged plasma around the planet. In other words, the activity of Enceladus does not remain confined to the moon itself. It influences the entire Saturn system. But perhaps the most exciting implication of these discoveries is what they reveal about the hidden ocean beneath the ice. If the plumes contain freshly erupted material from the ocean, then studying them may allow scientists to investigate the chemistry of that ocean without ever drilling through the ice. Future spacecraft could simply fly through the plumes again, collecting samples directly from the moon's interior. And within those samples may lie the answer to one of humanity's oldest questions. Are we alone in the universe? Or could life exist in the dark oceans of a tiny moon orbiting far from the sun? Enceladus may one day provide that answer. One of the most remarkable aspects of the Enceladus story is that even after the Cassini mission ended, the discoveries have not stopped. In fact, some of the most important insights about this mysterious moon have emerged years after the spacecraft was destroyed. When Cassini completed its mission in September of 2017, NASA made the difficult decision to send the spacecraft into Saturn's atmosphere, where it burned up and was destroyed. This maneuver, known as the grand finale, was performed intentionally. Scientists wanted to make absolutely certain that Cassini would never accidentally collide with Enceladus or another potentially habitable moon like Titan. If microscopic organisms from Earth had contaminated those environments, they could interfere with future studies searching for alien life. So Cassini's mission ended in a dramatic final plunge into Saturn. But the data it collected did not disappear. During its 13 years in the Saturn system, Cassini transmitted enormous amounts of information back to Earth. Scientists around the world are still analyzing those measurements today, and as computing power and analytical techniques continue to improve, researchers are able to extract new insights from the same data. In some cases, discoveries have emerged more than a decade after the measurements were originally taken. One fascinating example involves the temperature of Enceladus's surface. Early observations focused heavily on the South Pole, where the massive plumes were clearly visible. Thermal imaging instruments aboard Cassini detected strong heat signatures around the famous tiger stripe fractures. But more recently, scientists decided to revisit older observations of the North Pole. Using improved models and refined temperature analysis, researchers discovered something unexpected. The northern hemisphere of Enceladus also appears to be warmer than scientists had predicted. Although the temperature difference is small, only a few degrees, it suggests that the moon's internal heating may be more widespread than previously believed. This discovery raises an intriguing possibility. Instead of all geothermal activity being concentrated near the South Pole, Enceladus may possess a much more complex internal system distributing heat across the moon. If that is true, the hidden ocean beneath the crust could be interacting with the ice shell in multiple locations. And that would make the interior of Enceladus even more dynamic than scientists once imagined. Another surprising discovery came from examining the size and scale of the plumes themselves. When Cassini first observed the geysers erupting from the moon's south pole, they already appeared enormous. But new observations from the James Webb Space Telescope revealed something even more dramatic. Using Webb's powerful infrared instruments, astronomers detected a giant cloud of water vapor streaming from Enceladus into space. This plume was so large that it extended nearly 10,000 kilometers away from the moon. To put that in perspective, the plume stretched roughly 20 times the diameter of Enceladus itself. This discovery confirmed that the moon is continuously releasing enormous quantities of water into the Saturn system. And this water does not simply disappear into space. Instead, it forms a massive ring of particles and vapor surrounding Saturn, known as a torus. Over time, this material spreads throughout the planet's magnetosphere and even interacts with Saturn's upper atmosphere. In other words, Enceladus is not just an isolated moon. It is actively influencing the environment of the entire Saturn system. But the plume particles have another fascinating effect as well. As these tiny ice grains travel through Saturn's magnetic field, they lose electrons and become electrically charged. This creates streams of plasma that flow through the region around Enceladus. Scientists have discovered that these charged particles form enormous structures known as Alfvén wings, which extend hundreds of thousands of kilometers through space. These invisible plasma waves connect the moon directly to Saturn's magnetic field, forming a complex electromagnetic interaction between the moon and the planet. Even today, researchers are still trying to fully understand how these plasma structures behave. But they represent yet another example of how a relatively small moon can produce enormous effects across a planetary system. Despite all of these discoveries, one of the most intriguing questions about Enceladus remains unanswered. How long has the ocean existed beneath the ice? If the ocean formed only recently in geological terms, there may not have been enough time for life to emerge. But if the ocean has remained stable for hundreds of millions or even billions of years, then the chances of biological processes developing become much more significant. To investigate this question, scientists have turned once again to Cassini's thermal measurements. By studying the heat flowing through the moon's icy crust, researchers can estimate how much energy is being generated inside the moon. Recent studies suggest that the total heat output of Enceladus matches remarkably well with the energy expected from tidal heating models. This finding implies that the internal heating process may be stable over very long periods of time. If the ocean is continuously replenished with energy from the moon's interior, it could remain liquid for extremely long durations. And that stability is exactly what life requires. On Earth, life evolved gradually over immense spans of time. Chemical reactions slowly became more complex, eventually forming self-replicating molecules and primitive organisms. A similar process could theoretically occur anywhere the right conditions persist long enough. Water, energy, chemical ingredients, and time. Remarkably, Enceladus appears to possess all four of these factors. Because of this, scientists are now actively planning future missions that could return to this extraordinary moon. Several mission concepts have already been proposed. Some would involve sending a spacecraft back into orbit around Saturn, where it could perform repeated flybys of Enceladus and fly through the plumes again. With more advanced instruments than Cassini carried, these missions could analyze plume particles with far greater precision. Instead of simply detecting organic molecules, future probes might be able to identify specific biosignatures, chemical patterns that strongly suggest biological activity. Other mission concepts go even further. One idea involves landing a spacecraft directly on the icy surface near the South Pole. From there, the lander could collect fresh material falling back from the plumes and analyze it in a laboratory on board the spacecraft. Even more ambitious proposals imagine sending a robotic probe capable of melting its way through the ice. Such a machine, sometimes called a cryobot, would slowly descend through kilometers of frozen crust until it reached the hidden ocean below. Once inside the water, a small submersible robot could explore the alien sea directly. Of course, these types of missions are incredibly challenging. Drilling through thick ice on another world would require new technologies, enormous energy supplies, and careful planning to avoid contaminating the environment. But the potential rewards are extraordinary. If life were discovered beneath the ice of Enceladus, even microscopic life, it would fundamentally change our understanding of biology in the universe. It would mean that life can emerge in environments far beyond the traditional habitable zone around stars. Instead of requiring warm planets like Earth, life might thrive in hidden oceans beneath icy crusts scattered throughout the galaxy. And Enceladus would represent the first place where humanity discovered that we are not alone. For now, however, these questions remain unanswered. The plumes continue to erupt silently into space. The ocean remains hidden beneath kilometers of ice, and the secrets of this remarkable moon are still waiting to be uncovered. But one thing is certain: a world once dismissed as a frozen speck in the darkness has become one of the most exciting scientific mysteries in the entire solar system. And the story of Enceladus is far from over. For centuries, humanity has looked up at the night sky and wondered whether life exists anywhere beyond Earth. The planets of our solar system were the first places scientists searched for answers. Mars once appeared to be the most promising candidate. Its dry riverbeds and ancient lakes suggested that water had once flowed across its surface. If life had ever emerged there, traces might still remain beneath the Martian soil. But as our exploration of the solar system expanded, scientists began to realize that life might not be limited to planets alone. Some of the most intriguing environments may exist on icy moons, where vast oceans are hidden beneath thick shells of ice. Among these worlds, Enceladus has become one of the most compelling targets in the search for extraterrestrial life. This tiny moon, once overlooked and barely understood, now represents a place where many of the essential ingredients for life appear to come together. Liquid water exists beneath its frozen crust. Chemical elements necessary for biological processes are present within its ocean. Energy flows from the moon's interior through hydrothermal activity. And most importantly, these conditions may have existed for extremely long periods of time. Together, these factors create an environment that scientists refer to as potentially habitable. Habitability does not mean that life definitely exists there, but it means that the conditions are suitable for life to develop if the right processes occur. On Earth, life emerged relatively early in our planet's history. Within a few 100 million years after Earth formed, simple microorganisms had already appeared in the oceans. Over billions of years, these early life forms evolved into the incredible diversity of organisms we see today. But the origins of life remain one of the greatest mysteries in science. Exactly how simple chemical reactions became living systems is still not fully understood. One of the leading ideas is that life may have begun near hydrothermal vents on the ocean floor. These vents release hot, mineral-rich water into the surrounding ocean. The interaction between seawater and heated rock creates chemical gradients that can power complex reactions. In such environments, molecules may combine and reorganize themselves into increasingly complicated structures. Eventually, some of these structures may become capable of self-replication. Once a system can replicate itself and evolve through natural selection, life has effectively begun. If hydrothermal vents exist beneath the ocean of Enceladus, they could provide similar conditions. Water circulating through the rocky core would dissolve minerals and release hydrogen gas. These chemicals could serve as energy sources for primitive microorganisms. Over long periods of time, simple chemical systems might gradually evolve into biological ones. This possibility has motivated scientists to study Enceladus in extraordinary detail. One of the reasons Enceladus is such an appealing target for exploration is that its ocean is not completely sealed beneath the ice. Instead, the powerful plumes erupting from the South Pole act as natural conduits between the interior ocean and outer space. These geysers eject water vapor, ice particles, and organic molecules far above the moon's surface. When this material falls back down, some of it lands near the South Polar region, but much of it escapes into space, forming a ring of particles around Saturn. For spacecraft, this means that samples of the ocean are effectively being delivered directly into space. Future missions would not necessarily need to drill through kilometers of ice to study the ocean's chemistry. Instead, a spacecraft could simply fly through the plumes, capturing particles and analyzing them on board. This approach dramatically simplifies the search for biosignatures. If microbial life exists within the ocean, tiny fragments of biological material could potentially be carried upward within the plume particles. Sensitive instruments might detect amino acids, complex organic structures, or chemical patterns strongly associated with living systems. Several mission proposals have been developed around this idea. One concept involves an orbiter that would repeatedly pass through the plume, collecting samples during each flyby. Over time, the spacecraft could gather enough material to perform detailed chemical analyses. Another concept proposes sending a lander to the South Pole. This lander would sit near the tiger stripe fractures and collect fresh plume particles as they fall back onto the surface. With laboratory instruments on board, the lander could analyze these samples directly. But some scientists have proposed even more ambitious missions. One particularly fascinating idea involves sending a robotic probe capable of melting its way through the ice shell. This type of device, sometimes called a cryobot, would use heat generated by a nuclear power source to slowly descend through the frozen crust. As it melts the ice above it, the probe would gradually sink deeper and deeper into the moon. Eventually, after traveling through kilometers of ice, the cryobot could reach the hidden ocean itself. At that point, it might release a small, autonomous, submersible vehicle designed to explore the alien sea. Such a mission would represent one of the most extraordinary explorations ever attempted. For the first time in human history, a robot would enter an ocean on another world. The submersible could search for hydrothermal vents, study the chemistry of the water, and perhaps even capture images of the ocean environment. If life exists there, even in the form of microscopic organisms, such a mission might detect it. Of course, these ideas remain technologically challenging. The ice shell of Enceladus may be several kilometers thick, and the pressure within the ocean could be immense. Designing spacecraft capable of surviving these conditions would require major advances in engineering, but the scientific reward would be enormous. Discovering life beyond Earth would fundamentally change humanity's understanding of biology and the universe. It would demonstrate that life is not a rare accident limited to a single planet. Instead, life might emerge wherever suitable environments exist. And environments like Enceladus may be far more common than we once believed. In fact, the discovery of subsurface oceans beneath icy moons has transformed our view of the solar system. Jupiter's moon Europa is also believed to contain a vast ocean beneath its icy crust. Another moon, Ganymede, may possess multiple layers of water deep within its interior. Even Saturn's largest moon, Titan, has been shown to harbor an underground ocean beneath its thick atmosphere. These discoveries suggest that hidden oceans may be widespread among icy worlds orbiting giant planets. If each of these oceans contains the ingredients necessary for life, then the number of potentially habitable environments in the solar system increases dramatically. And beyond our solar system, astronomers have discovered thousands of planets orbiting distant stars. Many of these planets likely possess moons of their own. If icy moons with subsurface oceans are common throughout the galaxy, the number of possible habitats for life may be far greater than anyone imagined just a few decades ago. Enceladus, therefore, may represent only the beginning of a much larger story. It is a small world, but it has opened an entirely new frontier in planetary science. The search for life is no longer limited to warm, Earth-like planets orbiting within narrow habitable zones. Instead, life might flourish in dark oceans hidden beneath layers of ice, warmed by the gravitational forces of giant planets. In such places, sunlight may never reach the water, yet chemical energy flowing from the interior of a moon could still power ecosystems. And somewhere beneath the frozen crust of Enceladus, within an ocean that has likely existed for millions of years, complex chemistry may already be unfolding. Perhaps microscopic organisms are drifting through its dark waters. Perhaps entire ecosystems exist around hydrothermal vents on the ocean floor. Or perhaps the ocean remains sterile, waiting for the right conditions for life to begin. At this moment, we simply do not know. But what we do know is that Enceladus has transformed from an obscure moon into one of the most fascinating worlds in our solar system. Its geysers continue to erupt silently into space, carrying fragments of its hidden ocean into the darkness. And each of those tiny particles may contain clues about one of the greatest mysteries humanity has ever asked. Are we alone, or is life quietly thriving beneath the frozen surface of a distant moon orbiting Saturn? For now, Enceladus keeps its secrets hidden beneath the ice. But with every new mission, every new telescope observation, and every new analysis of the Cassini data, scientists move one step closer to finding the answer. And when that answer finally arrives, it may forever change the way we see our place in the universe. Despite everything scientists have already learned about Enceladus, one important truth remains. Our understanding of this extraordinary moon is still incomplete. The Cassini mission provided an incredible amount of data, but it also left scientists with many unanswered questions. The spacecraft was not designed specifically to search for life. Its instruments were powerful, but they were limited by the technology available when the mission was planned in the 1990s. Today, more than 2 decades later, scientists possess far more advanced tools and ideas for exploring worlds like Enceladus. And because of that, many researchers believe that returning to this moon could lead to one of the most important discoveries in the history of science. One of the biggest mysteries scientists still hope to answer concerns the true structure of the ocean beneath the ice. Current models suggest that Enceladus contains a global ocean surrounding a rocky core, but researchers are still uncertain about how deep that ocean might be. Some estimates suggest the water layer could be tens of kilometers deep, lying beneath an ice shell that may also be several kilometers thick. Within this hidden environment, water may be constantly circulating between the ocean and the rocky core below. If this circulation exists, it could transport minerals, gases, and heat throughout the ocean. This process would create chemical gradients, differences in energy and composition, that are extremely important for life. On Earth, many microorganisms survive by exploiting these chemical gradients. Instead of relying on sunlight, they use chemical reactions to produce energy. These reactions form the basis of ecosystems around hydrothermal vents deep in Earth's oceans. If similar conditions exist within Enceladus, they could support microbial life even in total darkness. But scientists still need more direct evidence. Cassini detected hydrogen gas and organic molecules in the plume particles, which strongly suggests that hydrothermal reactions may be occurring beneath the ice. However, researchers want to know exactly how intense those reactions might be. Are they strong enough to power long-lasting ecosystems? Or are they relatively weak processes that produce only limited chemical activity? Answering these questions will likely require new missions equipped with much more sensitive instruments. Fortunately, several space agencies are already considering future exploration of icy moons. One mission that will indirectly help scientists study environments like Enceladus is the Europa Clipper, which will explore Jupiter's icy moon Europa later this decade. Europa is believed to have an ocean beneath its ice, similar to Enceladus, though its surface is very different. Data from that mission will help scientists understand how subsurface oceans behave across the solar system. Another mission called JUICE, the Jupiter Icy Moons Explorer, will study several of Jupiter's moons, including Ganymede and Callisto. Although these missions are focused on Jupiter rather than Saturn, they will provide valuable information about how ocean worlds function. The knowledge gained from these missions could shape future plans to return to Enceladus. But several mission proposals are already being designed specifically for Saturn's mysterious moon. One idea is a spacecraft known as an Enceladus orbiter. This probe would travel to Saturn and remain in orbit around Enceladus for an extended period of time. From this position, the spacecraft could repeatedly fly through the plume jets erupting from the South Pole. Each pass through the plume would allow the spacecraft to collect tiny samples of ice and vapor. With modern instruments capable of detecting extremely small quantities of molecules, scientists could search for complex organic chemistry in unprecedented detail. They could also measure the isotopic composition of the water and organic molecules, clues that might reveal whether biological processes are involved. Another possible mission concept is known as a sample return mission. In this scenario, a spacecraft would capture particles from the plumes and store them inside a sealed container. The spacecraft would then return these samples to Earth, where scientists could analyze them using the most advanced laboratory equipment available. Laboratories on Earth are vastly more powerful than any instruments that can be placed on a spacecraft. Returning samples from Enceladus would allow researchers to perform extremely precise measurements of organic molecules, minerals, and chemical structures. Such a mission could potentially identify biological signatures that might otherwise remain undetectable. However, perhaps the most ambitious ideas involve exploring the hidden ocean directly. Scientists have proposed sending robotic probes capable of penetrating the icy crust. These probes, sometimes referred to as cryobots, would slowly melt their way through the ice using nuclear-powered heating systems. As the cryobot descends, it would carry instruments capable of measuring the temperature, chemical composition, and structure of the ice layers. Eventually, if the probe reached the ocean, it could release a small robotic submarine. This submersible would explore the dark waters beneath the ice. It could search for hydrothermal vents, map the ocean floor, and analyze the chemistry of the surrounding water. If life exists within the ocean, such a mission could potentially detect it directly. Of course, missions like this are incredibly challenging. The ice shell may be many kilometers thick, and the pressure within the ocean could be extremely high. Communication with a probe deep beneath the ice would also be difficult. Engineers would need to design systems capable of transmitting data through layers of ice back to the surface. Despite these challenges, the idea of exploring an alien ocean remains one of the most exciting possibilities in planetary science. If successful, such a mission would open an entirely new chapter in human exploration. But even before such missions become possible, scientists are continuing to make discoveries using the data already collected. In recent years, improved computer models have allowed researchers to simulate the interior of Enceladus with much greater accuracy. These simulations help scientists understand how heat flows through the moon's interior and how the ocean interacts with the rocky core. Some models suggest that the core of Enceladus may be porous, meaning that water can circulate through tiny channels in the rock. If this is true, the entire interior of the moon could function like a massive hydrothermal system. Warm water would flow through the rock, react with minerals, and then rise back into the ocean above. This constant circulation could maintain a steady supply of chemical nutrients in the ocean, and that environment could remain stable for extremely long periods. Another intriguing discovery involves the age of the plume activity. By studying the rate at which material escapes from Enceladus, scientists can estimate how long the geysers might continue erupting. Some estimates suggest that the plumes may have been active for millions of years. If that is correct, the ocean beneath the ice has likely existed for a very long time, and time, combined with water and chemical energy, is exactly what life requires. These discoveries have dramatically changed the way scientists think about habitable environments in the solar system. For decades, the search for life focused primarily on planets like Mars, but Enceladus has shown that even small icy moons can possess conditions suitable for life. In fact, ocean worlds may be among the most promising environments for biology. Hidden oceans are protected from radiation, shielded from extreme temperature changes, and supplied with chemical energy from planetary interiors. Such environments may be far more stable than the surfaces of many planets. And if subsurface oceans exist on multiple moons throughout the solar system, then the number of potentially habitable environments increases dramatically. Enceladus is therefore more than just an interesting moon. It represents a new category of world, a true ocean world, hidden beneath ice but rich with possibilities. The tiny geysers erupting from its south pole are like windows into this hidden environment. Each plume carries fragments of the ocean into space, offering scientists a rare opportunity to study the chemistry of an alien sea. And with each new discovery, the mystery of Enceladus grows deeper. Is its ocean simply a fascinating chemical laboratory? Or could it be home to living organisms drifting through dark waters beneath the ice? For now, that question remains unanswered. But the story of Enceladus is still unfolding, and somewhere within that distant ocean, beneath kilometers of frozen crust, the conditions for life may already exist, waiting to be discovered by the next generation of explorers. As scientists continue studying Enceladus, one realization has become increasingly clear. This small moon is not simply another frozen body orbiting a distant planet. Instead, it may represent an entirely new category of world, one where life could exist in places we once believed were impossible. For most of the 20th century, the search for life beyond Earth focused mainly on planets that resembled our own. Researchers believed that liquid water could exist only within a narrow region around a star, often referred to as the habitable zone. Within this region, temperatures allow water to remain liquid on the surface of a planet. But discoveries across the solar system have gradually reshaped that idea. Worlds like Enceladus have shown that liquid water does not necessarily require direct sunlight. Instead, powerful internal forces can maintain oceans beneath thick layers of ice, even in the coldest regions of space. This realization has expanded the potential habitats for life dramatically. Enceladus is now considered part of a growing class of objects known as ocean worlds. These are bodies that contain vast subsurface oceans beneath icy crusts. Some of these oceans may contain more water than all of Earth's oceans combined, and Enceladus is not alone. Jupiter's moon Europa is believed to harbor a global ocean beneath its fractured icy surface. Another moon, Ganymede, likely contains multiple layers of water deep beneath its crust. Even Saturn's moon Titan is thought to hide an ocean beneath its thick atmosphere and icy shell. These discoveries suggest that oceans may be extremely common throughout the solar system. If that is true, the number of environments where life might potentially develop increases dramatically, and Enceladus may be one of the most accessible of these worlds. Unlike many other ocean worlds, Enceladus offers scientists a remarkable advantage. The ocean beneath its ice is not completely sealed away. Instead, the moon continuously ejects material from its interior into space through the massive geysers at its south pole. Each eruption sends tiny particles of water, ice, and organic molecules high above the surface. Some of this material escapes entirely, forming Saturn's E-ring. For scientists, these plumes act almost like natural sampling systems. Instead of drilling through kilometers of ice, a spacecraft can simply fly through the plume and collect particles directly from the ocean below. This unique situation has transformed Enceladus into one of the most important targets for future exploration. But there is still much we do not know about the moon's hidden ocean. For example, scientists are still uncertain about the exact thickness of the ice shell covering the ocean. Estimates vary depending on the region of the moon. Near the South Pole, where the tiger stripe fractures are located, the ice may be relatively thin, perhaps only a few kilometers thick. But in other regions, the crust could be much thicker. Understanding this structure is important because it influences how heat and chemicals move between the ocean and the surface. Another key question involves the stability of the hydrothermal systems inside the moon. If water is circulating through the rocky core of Enceladus, it may be reacting with minerals and releasing gases such as hydrogen. This hydrogen could act as a fuel source for microbial life, but scientists want to know how long these hydrothermal processes might continue. If they are short-lived events, the ocean might not remain chemically active long enough for life to develop. However, if these reactions have been occurring for millions or even billions of years, they could provide a stable energy source capable of sustaining ecosystems. Recent studies suggest that tidal heating inside Enceladus may be capable of maintaining these processes for very long periods. The gravitational interaction between Saturn and its moons constantly flexes the interior of Enceladus, producing friction that generates heat. This energy could keep the ocean warm and maintain hydrothermal activity beneath the crust. If this heating remains stable, the ocean could persist for enormous spans of time. And time is one of the most important ingredients in the development of life. Life on Earth did not appear instantly. Instead, it emerged gradually through complex chemical processes that unfolded over hundreds of millions of years. Given enough time, simple molecules can combine to form increasingly complex structures. Eventually, these structures may become capable of replication and evolution. At that point, biology begins. Whether such a process could occur within the ocean of Enceladus is still unknown, but the chemical ingredients appear to be present. Cassini detected organic molecules, hydrogen gas, and other compounds associated with hydrothermal chemistry. More recently, scientists confirmed the presence of phosphorus, completing the set of key elements believed to be essential for life. These discoveries suggest that the ocean beneath Enceladus may contain a rich mixture of chemical building blocks, but chemistry alone does not guarantee life. Scientists must also determine whether the environment inside the moon is stable and suitable for biological processes. To answer these questions, researchers are now studying Enceladus using both spacecraft data and computer simulations. Advanced models allow scientists to recreate the interior conditions of the moon, including temperature, pressure, and chemical reactions within the ocean. These simulations help researchers understand how water circulates between the rocky core and the icy crust above. Some models suggest that the core of Enceladus may be highly porous, allowing water to flow through networks of tiny channels within the rock. This circulation could create widespread hydrothermal activity across the ocean floor. If that is true, the interior of Enceladus could be filled with chemical energy sources capable of supporting microbial ecosystems. Another intriguing question concerns the diversity of environments within the ocean. On Earth, life thrives in a wide range of conditions, from warm, shallow waters to deep hydrothermal vents. If Enceladus contains a large ocean, it may also contain multiple types of environments with different chemical conditions. Some regions might be relatively calm and cold, while others could be dominated by active hydrothermal systems. These variations could allow different types of chemical processes to occur simultaneously within the ocean, and that diversity could increase the chances that life might develop. Beyond the search for life itself, Enceladus also offers scientists an opportunity to study the evolution of ocean worlds. Understanding how oceans form and persist beneath icy crusts could help researchers interpret similar environments throughout the galaxy. Astronomers have already discovered thousands of planets orbiting other stars. Many of these planets may possess moons of their own. If icy moons with subsurface oceans are common, then ocean worlds could exist across countless planetary systems. And if life can emerge in such environments, it might be far more widespread than we once believed. Enceladus, therefore, represents more than just a single location in the solar system. It serves as a gateway to understanding how life might arise in unexpected places throughout the universe. In the coming decades, future missions will likely return to Saturn and its moons. New spacecraft equipped with advanced instruments will fly through the plumes of Enceladus, searching for increasingly detailed chemical clues. Perhaps they will detect complex molecules that strongly suggest biological activity. Or perhaps they will find clear biosignatures that confirm the presence of life. If that day comes, it will mark one of the most profound discoveries in human history. For the first time, we would know that life exists beyond Earth. But even if Enceladus turns out to be sterile, the knowledge gained from studying this remarkable moon will still reshape our understanding of planetary science, because Enceladus has already revealed something extraordinary. Even in the cold darkness far from the Sun, worlds can remain active, dynamic, and filled with hidden oceans. And within those oceans, the conditions for life may quietly exist. As scientists continue their search, Enceladus remains one of the most promising places in our solar system to look for an answer to one of humanity's oldest questions. Are we alone? Or could life be waiting beneath the ice of a distant moon orbiting Saturn? As our understanding of Enceladus continues to grow, the moon has slowly transformed from a scientific curiosity into one of the most important destinations in planetary exploration. What once appeared to be a quiet, frozen satellite has revealed itself as a world filled with movement, chemistry, and hidden oceans. But perhaps the most remarkable aspect of Enceladus is how much of its story has been uncovered without ever touching its surface. The Cassini spacecraft never landed on the moon. It never drilled through the ice or explored the ocean directly. Instead, the spacecraft simply passed through the giant plumes erupting from the South Pole, collecting particles as they blasted into space. And from those tiny grains of ice, scientists were able to reconstruct the hidden environment beneath kilometers of frozen crust. Few places in the solar system offer such a direct window into an underground ocean. Each plume eruption acts like a natural fountain, sending material from the interior of the moon far into space. These particles carry chemical fingerprints from the ocean below, allowing researchers to study the composition of an alien sea without ever drilling through the ice. But while the plume particles reveal much about the chemistry of the ocean, they cannot answer every question. To fully understand Enceladus, scientists need to know more about the structure of the ice shell, the depth of the ocean, and the processes happening at the ocean floor. For example, researchers are still trying to determine exactly how thick the ice crust might be. Near the South Pole, where the famous tiger stripe fractures stretch across the surface, the ice appears to be relatively thin. Heat rising from the interior weakens the crust, allowing cracks to form and water to escape through the geysers. In some models, the ice near the South Pole may be only a few kilometers thick, but in other parts of the moon, the ice shell could be significantly thicker, perhaps tens of kilometers deep. This variation in thickness may help explain why the plumes erupt specifically from the South Polar region. The fractures there may connect directly to pockets of liquid water beneath the crust, forming channels through which pressurized water can escape. As tidal forces from Saturn flex the moon's interior, these fractures open and close slightly. Each cycle may allow bursts of water vapor to shoot upward into space. Over time, the escaping material builds the enormous plume clouds that Cassini observed. But scientists are also interested in how the ocean itself behaves beneath the ice. Is it calm and relatively uniform, or is it filled with currents and chemical gradients similar to Earth's oceans? If hydrothermal vents exist on the ocean floor, they may release warm water rich in minerals into the surrounding ocean. This heated water would rise, creating circulation patterns within the ocean. Such circulation could distribute nutrients and energy throughout the environment. On Earth, ocean circulation plays a major role in maintaining ecosystems. Warm water rising from hydrothermal vents supports entire communities of organisms that rely on chemical energy rather than sunlight. If Enceladus contains similar circulation systems, the hidden ocean could be far more dynamic than scientists originally believed. Another important factor scientists are studying is the age of the ocean. Determining how long Enceladus has possessed liquid water is crucial in estimating whether life might have had time to emerge. If the ocean formed only recently, chemical processes may still be in their early stages. But if the ocean has existed for hundreds of millions or billions of years, the chances of biological evolution become far greater. Evidence gathered from Cassini's thermal measurements suggests that tidal heating inside the moon could maintain liquid water for extremely long periods. The gravitational interaction between Saturn and Enceladus continually flexes the moon's interior. This constant deformation generates heat through friction. As long as this tidal interaction remains stable, the interior of the moon may continue producing enough energy to keep the ocean from freezing. And because the orbit of Enceladus is influenced by neighboring moons, this heating process may have remained active for a very long time. If that is true, then the hidden ocean beneath Enceladus may be one of the most stable aquatic environments in the solar system. But even with all these discoveries, the biggest question still remains unanswered. Does life exist there? For scientists searching for life beyond Earth, Enceladus represents an extraordinary opportunity. Unlike Mars, where any life would likely be buried deep beneath the surface, Enceladus is actively ejecting material from its interior. Those plume particles provide a natural pathway for studying the ocean's chemistry. Future spacecraft equipped with highly sensitive instruments could analyze these particles in much greater detail than Cassini was able to. Modern spectrometers could search for amino acids, the building blocks of proteins. They could detect specific patterns in organic molecules that indicate biological activity. They might even identify fragments of complex structures, such as cell membranes or other molecular arrangements associated with life. But even if future missions do not find direct evidence of life, studying Enceladus will still provide invaluable insights into the formation of ocean worlds. Understanding how water interacts with rock, how tidal heating generates energy, and how complex chemistry evolves within subsurface oceans will help scientists interpret many other environments throughout the solar system. Because Enceladus is not the only world where hidden oceans exist. Jupiter's moon Europa is believed to contain an ocean larger than all of Earth's oceans combined. Beneath its cracked, icy surface, tidal heating from Jupiter may maintain liquid water and hydrothermal activity. Ganymede, the largest moon in the solar system, may possess multiple layers of water trapped beneath its crust. Even Saturn's moon Titan may contain a deep underground ocean beneath its thick atmosphere of nitrogen and methane. These discoveries have dramatically changed the way scientists think about planetary habitability. In the past, the search for life focused almost entirely on planets located within narrow, habitable zones around stars. But ocean worlds like Enceladus demonstrate that life might exist far beyond those traditional boundaries. Instead of sunlight, these worlds rely on internal energy generated by gravitational forces. Instead of surface oceans warmed by starlight, they contain dark seas hidden beneath thick layers of ice. Yet within those hidden oceans, the conditions for life may still exist. Water, energy, chemical building blocks, and time. These four ingredients are widely considered the fundamental requirements for life as we understand it. Remarkably, Enceladus appears to possess all of them. This combination makes the Moon one of the most promising places in the solar system to search for extraterrestrial biology, and that realization has transformed the priorities of planetary exploration. Scientists are now actively developing new mission concepts designed specifically to study ocean worlds. Some of these missions will return to Enceladus. Others will explore Europa, Titan, and other icy moons. Each mission will help researchers understand how these environments function and how common they may be across the galaxy. But even before those missions arrive, Enceladus continues to reveal new secrets through the data already collected. Each reanalysis of Cassini's measurements provides deeper insights into the chemistry and physics of the Moon, and every discovery brings scientists one step closer to understanding whether life could truly exist beneath the ice. For now, Enceladus remains a distant and mysterious world. Its bright, icy surface reflects sunlight across the darkness of the Saturn system. Beneath that frozen crust lies an ocean that may have existed for millions of years. And deep within that ocean, hidden far from sunlight and warmth, the chemistry of life may already be unfolding. The plumes rising from the South Pole continue to spray particles of that ocean into space. Each tiny grain of ice carries a fragment of the Moon's hidden story. And somewhere within those particles may lie the answer to one of humanity's oldest questions. Is life unique to Earth? Or is it quietly waiting beneath the frozen surface of a distant moon orbiting Saturn? For now, the ocean of Enceladus remains silent, but one day, future explorers may finally uncover what lies within its dark waters. As scientists continue to study Enceladus, the Moon has gradually become more than just a fascinating object of research. It has become a symbol of how quickly our understanding of the universe can change. Only a few decades ago, Enceladus was considered a small, unremarkable satellite orbiting Saturn. It appeared to be frozen, inactive, and scientifically unimportant compared with larger moons like Titan. But discoveries from the Voyager missions, followed by the extraordinary observations from Cassini, revealed something completely unexpected. Beneath the icy crust of this tiny moon lies a hidden ocean. From deep fractures near the South Pole, enormous geysers eject water and ice into space. Organic molecules, hydrogen gas, and essential chemical elements have been detected within the plume particles, and evidence now suggests that hydrothermal activity may exist on the ocean floor. Together, these discoveries have transformed Enceladus into one of the most promising environments for life in the entire solar system. But perhaps the most important lesson from Enceladus is how much remains unknown. Even after decades of observation and years of analyzing Cassini's data, scientists are still uncovering new clues about the Moon's interior. One reason for this is the sheer complexity of the environment beneath the ice. Enceladus is not simply a frozen shell floating above a quiet ocean. Instead, the entire moon appears to function as a dynamic system. Heat generated by tidal forces flows upward from the rocky core. Water circulates through cracks and pores within the interior rock. Chemical reactions between water and minerals release gases such as hydrogen. These gases mix with organic molecules within the ocean, creating a chemically rich environment. Eventually, some of this material escapes through the tiger stripe fractures, erupting into space as the giant plumes observed by Cassini. This cycle connects the deep interior of the moon to the surface and beyond. It is a process that may have been occurring for millions of years, and during that time, countless chemical reactions may have taken place within the ocean. If the conditions are stable and energy sources remain available, those reactions could gradually become more complex. Over long periods of time, chemistry might evolve toward biology. Of course, scientists must remain cautious when discussing the possibility of life on Enceladus. At present, there is no direct evidence that living organisms exist there. The molecules detected by Cassini are intriguing, but they could still be produced by purely geological processes. Nevertheless, the environment beneath the ice possesses many of the characteristics that scientists associate with habitable environments. Liquid water is present. Chemical energy appears to be available through hydrothermal reactions. Organic molecules exist within the ocean, and the system may have remained stable for very long periods. These factors combine to create conditions that are at least capable of supporting life, and that possibility has captured the imagination of scientists and the public alike. Future missions will likely play a crucial role in resolving these questions. Several proposals currently being studied focus specifically on returning to Enceladus with more advanced instruments. One concept involves a spacecraft that would repeatedly fly through the plumes, capturing ice particles and analyzing them in real time. Modern spectrometers could search for complex organic structures far more effectively than Cassini's instruments were able to. Researchers could also measure subtle chemical signatures that might indicate biological processes. For example, certain ratios of isotopes within organic molecules can reveal whether those molecules were produced by living organisms. Another mission concept proposes placing a lander directly on the icy surface near the South Pole. From that location, the lander could collect fresh plume material as it falls back onto the moon. Because the plumes originate from the interior ocean, these particles may contain samples of water that has recently been expelled from beneath the ice. Analyzing those samples with onboard instruments could provide extremely valuable information about the chemistry of the ocean. Some scientists have even proposed building a spacecraft capable of returning plume samples to Earth. In such a mission, captured particles would be sealed inside a secure container and transported back to laboratories on our planet. Earth-based laboratories possess far more powerful analytical tools than any instruments that can currently be sent into space. If plume samples were returned, researchers could examine them in extraordinary detail. They might search for amino acids, complex organic molecules, or other biosignatures that could indicate biological activity. But perhaps the most ambitious ideas involve exploring the ocean itself. The thought of sending a probe beneath the ice of Enceladus may sound like science fiction, Yet engineers have already begun studying how such missions might work. One concept involves a nuclear-powered probe that would slowly melt its way through the ice shell. As it descends, the probe would transmit data about the structure and composition of the ice layers. Eventually, it might reach the hidden ocean below. Once inside the water, a small robotic submersible could explore the alien sea. This underwater vehicle might search for hydrothermal vents, study the chemistry of the water, and scan the ocean floor. If life exists within the ocean, such a mission could potentially detect it directly. Of course, building and launching such a mission would be incredibly challenging. The ice shell may be several kilometers thick, and communication with a probe deep beneath the surface would require advanced technologies. But the potential reward, discovering life beyond Earth, would be one of the most significant achievements in human history. Even if life is not found, the exploration of Enceladus would still provide remarkable insights into the nature of ocean worlds. By studying this moon, scientists can better understand how water, rock, and energy interact within planetary bodies. This knowledge will help researchers interpret similar environments across the solar system and beyond. Because Enceladus may not be unique, astronomers now believe that icy moons with hidden oceans may be common throughout the universe. Many exoplanets discovered around distant stars likely possess moons of their own. If those moons contain subsurface oceans warmed by tidal heating, they could potentially support life as well. In that sense, Enceladus may represent a small example of a much larger class of habitable environments scattered across the galaxy. Studying this moon therefore helps scientists understand how life might emerge in places very different from Earth. The quiet geysers erupting from Enceladus's south pole are more than just beautiful natural phenomena. They are signals from a hidden ocean deep beneath the ice. Each plume carries particles of that ocean into space, offering scientists a rare opportunity to study an alien environment. And within those particles may lie the chemical clues needed to answer one of the most profound questions humanity has ever asked. Are we alone in the universe? Or does life exist elsewhere, perhaps hidden beneath frozen surfaces on distant worlds? For now, the ocean of Enceladus remains concealed beneath its brilliant white crust. The geysers continue to erupt silently into space, scattering fragments of the moon's hidden interior across the Saturn system. But with each new discovery, scientists move closer to understanding what lies beneath the ice. And one day, when a new generation of spacecraft returns to Enceladus, humanity may finally learn whether life exists within its dark ocean. Until that moment arrives, this small moon will remain one of the most mysterious and fascinating places in our solar system. As our journey through the mysteries of Enceladus comes to an end, it becomes clear that this small, icy moon has completely reshaped how scientists think about life in the universe. For centuries, humanity believed that life could only exist on warm, Earth-like planets bathed in sunlight. Oceans, forests, and atmospheres seemed essential for biology to emerge and survive. The idea that life might exist in darkness, far from any star's warmth, once seemed almost impossible. But Enceladus quietly challenges that assumption. Orbiting nearly 1.4 billion kilometers from the Sun, This tiny moon receives only a fraction of the sunlight that reaches Earth. Its surface temperature averages around minus 200 degrees Celsius, cold enough to freeze almost any known substance solid. At first glance, it appears to be one of the most hostile environments imaginable. Yet beneath that frozen surface lies a hidden ocean, an ocean warmed not by sunlight, but by the immense gravitational forces of Saturn. Each time Enceladus orbits the giant planet, Saturn's gravity stretches and squeezes the moon slightly. This constant flexing generates heat deep inside the interior, preventing the subsurface ocean from freezing solid. Over millions of years, that tidal heating has created an environment where water, rock, and chemistry interact in ways remarkably similar to conditions found in some of Earth's deepest oceans. And that realization has fundamentally changed the search for life. Scientists now understand that habitable environments do not necessarily require sunlight or warm planetary surfaces. Instead, life may exist anywhere that three basic ingredients are present: liquid water, energy, and complex chemistry. Enceladus appears to have all three. Its global ocean may extend beneath most of the moon's icy crust, forming a vast reservoir of liquid water. Hydrothermal activity at the ocean floor likely produces chemical energy through reactions between water and rock. And organic molecules, essential building blocks for life, have already been detected within the plumes erupting from the South Pole. Together, these discoveries make Enceladus one of the most compelling places to search for life beyond Earth. But even if no life exists there, the moon still represents an extraordinary scientific treasure, because Enceladus provides a rare opportunity to study an ocean world without needing to drill through kilometers of ice. The towering plumes erupting from the tiger stripe fractures act like natural fountains, carrying particles from the hidden ocean into space. These tiny grains of ice contain chemical information from deep inside the moon. When Cassini flew through the plumes, its instruments captured those particles and analyzed their composition. From those fleeting encounters, scientists were able to reconstruct an entire hidden world beneath the surface. They discovered salts that indicate contact between ocean water and rock. They detected organic molecules that could form the building blocks of life. They measured molecular hydrogen, suggesting that hydrothermal reactions are occurring on the ocean floor. Each piece of data provided another clue about the environment beneath the ice. And yet, Cassini's discoveries may represent only the beginning, because the instruments aboard that spacecraft were designed decades ago, long before scientists fully understood the importance of Enceladus. Future missions will carry far more advanced technology. Sensitive mass spectrometers could identify complex organic molecules within the plume particles. High-resolution analyzers might detect amino acids, lipids, or other chemical structures associated with biological systems. Some instruments may even be capable of identifying subtle patterns in molecular distributions that could indicate biological processes. And if those signatures are found, the implications would be extraordinary. Discovering life in the ocean of Enceladus would mean that biology can emerge in environments far beyond Earth. It would suggest that life may be common throughout the universe, developing wherever the right conditions exist. But even if those missions find only complex chemistry, rather than living organisms, the scientific value of Enceladus will remain immense, because studying this moon helps scientists understand how planets and moons evolve. It reveals how gravitational forces can generate internal heat. It shows how water and rock interact to produce chemical energy. And it demonstrates that oceans can exist in places where sunlight never reaches. These insights extend far beyond our solar system. Astronomers have now discovered thousands of planets orbiting distant stars, many of which may possess moons of their own. If some of those moons contain subsurface oceans similar to Enceladus, they too could host environments capable of supporting life. In that sense, Enceladus may represent a small example of a much larger population of hidden ocean worlds scattered across the galaxy. Each one may contain its own dark seas beneath layers of ice. Each one may possess the chemistry necessary for life, and somewhere among them, biology may already be thriving. For now, however, Enceladus remains distant and silent. Its icy surface reflects sunlight across the vast darkness of the Saturn system. The geysers near its south pole continue to erupt, sending streams of water vapor and ice high into space. Those plumes slowly replenish Saturn's faint E-ring, spreading particles of frozen ocean throughout the planet's surroundings. From a distance, the moon appears peaceful, almost delicate, yet beneath that quiet exterior lies a dynamic and active world, a world of underground oceans, of chemical reactions occurring in darkness, of warm hydrothermal vents hidden beneath kilometers of ice, and possibly, just possibly, a world where life may exist far from the warmth of any sun. One day, new spacecraft will return to Enceladus. They will fly through the plumes again, this time carrying instruments capable of detecting the faintest traces of biological chemistry. Some may even land on the surface, collecting fresh particles of ice that have fallen from the erupting geysers. And perhaps many decades from now, humanity may send a probe deep beneath the frozen crust to explore the alien ocean itself. If that day comes, we may finally see what lies beneath the ice. We may discover ecosystems thriving around hydrothermal vents, illuminated only by faint chemical reactions. Or we may find that Enceladus is a world where the ingredients for life exist, but biology has never taken hold. Either outcome would transform our understanding of the universe, because Enceladus reminds us that the cosmos is filled with hidden places, worlds that appear cold and lifeless from afar, yet may harbor extraordinary environments beneath their surfaces. And somewhere within those hidden oceans, the story of life beyond Earth may already be unfolding. For now, we can only watch from afar as this small moon continues its silent orbit around Saturn. Its geysers erupt patiently into the darkness. Its ocean remains concealed beneath layers of ice, and its mysteries wait for the explorers who will one day return to uncover them. Until then, Enceladus stands as one of the most remarkable worlds ever discovered. A frozen moon with a warm ocean beneath its surface, quietly reminding us that the universe may hold far more life than we once imagined.